And we are back. All right, today we're going to talk about the different particles that make up the atom, or the subatomic particles. So the last two that we're going to talk about here are both found in the nucleus. So the protons and neutrons are found in the nucleus of an atom. Okay, and each of these have their own unique abbreviation and symbol. So protons found in the nucleus have a positive charge. So the abbreviation for a proton is lowercase p followed by a superscript plus sign to indicate it's a proton and it's positively charged. And then neutrons, also found in the nucleus, have no charge or are neutral. So the abbreviation for the neutron is lowercase n with a 0 as a subscript to indicate that it has no charge, that it's neutral. And then finally, electrons are found outside the nucleus, around the rest of the atom, and they're negatively charged. So the abbreviation for the electron is a lowercase e followed by a negative sign. Okay, so what I want to go over here is the incredibly small size of the nucleus in comparison to the rest of the atom. So if the nucleus, if it were the size of a ball bearing or marble, then the rest of the atom would essentially be the size of a large football stadium. So, both the protons and neutrons are found in this tiny nucleus, and for most atoms that's around a magnitude of times 10 to the negative 13th centimeters. And even if the size of the nucleus was just this little dot, it would be like the entire size of the atom would be the size of the entire board on the classroom. So like the electrons are all around the outside of the atom, so all the electrons are around the outside here. And that magnitude, the entire size of the atom, is around 10 to the negative 8th centimeters. So I want to stress the nucleus is very, very small compared to the overall size of the atom. However, it does make up most of the mass. So if you look at this little chart, you look at these two masses of the proton and neutron, they're very, 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 very close together. They're 0.002 apart. So I want you to assume that that mass ratio is 1:1, so that the proton and the neutron have the same mass. And then if you look at the mass of the electron, now that's times 10 to the negative 31st, so that mass is incredibly small in general, and it's still incredibly small in comparison to both the mass of the proton and the neutron. So we are going to assume the mass of the electron, since it's so small, we're going to assume it's negligible, that mass. So we are going to ignore it since it's so small. Okay, then the relative charges, the neutron has no charge. Then the two charges of the proton and the electron are equal and opposite. And we each assign those charges a magnitude of 1. The reason we do that, the actual charge of both an electron and proton is 1.6 times 10 to the negative 19th coulombs, which is what we use to measure charge. So it's much harder to work with that number rather than just assigning them easy to work with charges of 1. Okay, so in the nucleus, you find the protons and neutrons. And then outside the nucleus, you find the electrons. Okay. So that means the nucleus is very dense since it contains all the mass, or almost all of the atom's mass. So that means if a piece of nuclear material, if you had just the size of a pea, so about a marble, it would weigh 250 million tons. So even though that nucleus contains a very small amount of space, it is extremely dense, and even a small amount of it would weigh quite a bit. So even though all that mass is contained in the nucleus, what really matters when reacting or interacting with other atoms is the electrons. So the electrons, and especially the outer electrons, and we're going to talk about how those have a specific name. So the outer electrons, that's what determines the properties of an atom. Okay, so how it interacts with other atoms, or the electrons, since they're on the outside, those are the parts that intermingle with other atoms. So this is a good visual of an atom. The fact that the nucleus is very small, and the fact that the rest of the atom is mostly empty space. So it's either empty space or electrons. So the majority of the atom is empty space. So now, with these different subatomic particles, we want to be able to identify different atoms. So first off, how the periodic table is organized is based on listing sequentially those atoms in atomic number. And what that is equivalent to of each atom is the number of protons. Okay, so each atom, or each number you see at the top of each box on the periodic table, the atomic number, that's its number of protons. Now, one thing that is not on the periodic table is the mass number. And that mass number is simply those two subatomic particles that make up most of the mass of the atom, the number of protons plus the number of neutrons. So one thing I want to stress, that mass number is not on the periodic table. What is on the periodic table is something different. That's average atomic mass. So mass number, since it's simply protons plus neutrons, that will always be a whole number. Okay? Then within a particular atom, we have what are called isotopes. So it's the same atom, because it has the same number of protons. So it has the same atomic number, but it has a different number of neutrons. So that means it has a different mass number. So same atomic number, but different mass number. So the same atom, since they have the same number of protons, they have a different mass number. And in an atom, the only thing that can change is the number of neutrons. So the number of electrons is still the same, so its chemical properties are still essentially the same. And then finally, most elements contain mixtures of these isotopes. There are a couple elements in which there's only one isotope, so that number at the bottom of each box on your periodic table is a whole number. But if you look at the majority of those numbers are decimals. That's because that average atomic mass is an average of all those different isotopes of a particular element. Okay, so if we look at a particular two different isotopes of sodium, we need ways to differentiate. How do we tell the difference between these two isotopes? And first off, for all atoms, and then in the next section we will talk about ions, which are charged particles. For atoms, since all atoms are neutral, the number of protons must equal the number of electrons, because protons have a positive one charge. In order to balance out that charge, there has to be the same number of electrons. Okay, so if you look at these two different isotopes of sodium. So automatically when we say sodium, you should find Na on your periodic table. The number at the top in that little box for sodium is 11. So that means 11 protons. So that means in each isotope, sodium has to have 11 protons. Then, since it's an atom, that number of protons has to equal the number of electrons. But here, in this isotope, there's 12 neutrons. Here, there's 13 neutrons.